You guys, so let's start. So last time I started to see cup or and also transform. So let me make very quick from here. We have been using inductor for now several weeks. In inductor as a device, it looks like as you see here, it has a magnetic metal core. Also, it has a wire. This wire, you just turn it around this way, okay? And we have here one conductor, we call it L, inductance. And as we explained before, the higher the inductance, the more energy it can absorb, because that's what you need to keep in mind. And that's what I'm gonna teach in details in the coming chapter as well. There is a big difference between capacitor and inductor at one hand and resistor at the other hand. There's a big difference between them. As you will understand better in the coming chapter, actually resistors are consuming, they consume energy. They consume energy. However, inductors and capacitors actually they store and they release energy. They don't consume. They store and release. Okay. Anyway, also we are familiar with this one here. The voltage across the inductor is actually equal to LdI by dt or NdPhi by dt. And the, if the circuit I have explained several examples in case of each circuit. You have an each circuit with inductor. Okay, so the each circuit inductor, the way you can analyze it, as I explained, you just replace the inductor with an impedance like J omega L, and then you use it. I have explained for example for inductor here. Now I'm gonna I will mix. I already explained last time, but I wanna just make very quick revision for coupled inductors and the transformers. And then I think what we have in this chapter, I'm gonna explain examples. Until now, I didn't explain if the circuit has coupled inductor, how can you analyze it? What I did, if the circuit has inductors, how can you analyze it? Okay, so that's what I'm going to explain. How can you analyze AC circuits if they have coupled inductors and also transformers? Okay? For coupled inductor, as I told you, you actually couple or you connect the circuits, but not using the electrical connection. You connect the circuit using magnetic. Okay, and the way it has been done, as I told you, here in this material, the magnetic field or the flux is gonna go through this material this way, and because of that, there will be a voltage induced here. Okay, so that's why I'm saying these two circuits are connected together or coupled. Use the word coupled. They are coupled together, but they are not connected using electrical line or electrical connection. It's connected using magnetic field. That means anything happens here at this side, it will be reflected on the other sides, okay? Because they are connected using magnetic field. Anyway, and then I told you, now I'm gonna change the formula we used before. If the inductor is not is just a single inductor or normal inductor, okay? And here the formula will be a little bit different. Look, this is the formula we use. This is the relation between G and I. Here in this case, the voltage V1, here I'm going to call the voltage here V1, V2, I1, I2. So the voltage V1 should equal L1 dI1 dt. So this one is exactly similar to this one. So I have to add or subtract the impact of the other inductor on this one. So they have to impact each other. Why? Because they are connected using the same magnetic. Okay, because of this magnetic force, there is some impact. So every inductor has to impact the other one because they share the same magnetic force. Okay? Same thing here. So this one in here because M here is going to be, we call it M, actually we call it mutual inductance, which actually can reflect the impact of one inductor on the other. So we have only one M. So here, this inductor has L1, this one has L2, but between them we have M, okay, only one M. Same thing for the other side here, V2 should equal L2 GI2 CG. So you can see here, it's exactly the same formula we used to before. Makes sense, right? But I have to add or subtract the impact of the other one, okay? Which is going to be plus or minus M I1. That's why you see here, this is V2. This one has to be number 1. This is number 1, so this one has to be number 2 because this is a mutual impact. Okay? That's why here, because they are coupled. If they are not coupled, we should use this. Okay. So as you will see right now, I want to show you the difference between what we have done when you analyze a circuit that has coupled inductors, what we have done before, and what we are going to do right now. What we've done before, C should equal J omega L because it's coming from this one. You can tell now because I changed it now the relation. We have two parts. Also, when you convert to the complex domain, as you see here, also we have two parts. J omega L1 I1, which is similar to what we did before. This times I, it's exactly the same thing. And this one coming from here, this differentiation. Next one, J omega M I2. Okay, I2. Same thing, the voltage across the second inductor, V2, is equal J omega L2 I2, yeah? And plus or minus J omega M I1. So always, when you have M, it has to be the other one, because this M is just for the impact of the other inductor. Okay? Don't be confused. That's what we will do. Or this is the information we have. So I should not use this one anymore. Okay, so it has to be replaced by these ones. That is the information we have right now. I will give you some examples to see how we are going to use this one. Okay, when you analyze circuits. One more thing, very simple. In any circuit, how can you tell if this is just an inductor or this is a mutual inductor? Okay, very simple. You can see here if it is a coupled inductor. In case of coupled inductor, I'm gonna make arrow this way, and then I'm gonna take M here. Okay, just to tell you if they are coupled. They are coupled. They impact each other. Okay. So this is one. This is how it will be done, or this is how can you tell. The other thing also, as I told you last time, how can you tell if you should, because you are telling us plus or minus. Okay. So maybe I need to go to the slides. So it depends on the direction, as I explained to you last time. It depends on the direction of the wiring. Okay. And again, this is not something you should guess, has to be given to you. Yeah, so here I think I have this. Yeah, if you see here, usually we use this dot convention. And this dot convention just to tell you the direction. So here, so as you see here the direction of this wire is going to be this way, okay? In both cases. But the other one, look here, this direction is this way, but this one is this way. Anyway, regardless, okay? So again, what I want to say, the way you are gonna turn these wires, okay, is gonna tell you if the induced voltage is gonna access the original voltage or it's gonna plus or minus. Plus means it's gonna access, it's gonna be the same polarity, or it's gonna be other polarity. Okay. So so here, if the current here enters, so if the current enters the dot in the two cases, or it output the dot in the two cases, that means they are positive, they should assist each other. But if the current is entered in one direction and output here in the other direction, so here this one output, so actually this should be minus. Okay, they are not helping each other. Okay? You will see now in the examples. Now, before I give you examples on coupled inductor, where in case of coupled inductor, we will use you again. What we are going to use, I will choose examples. But now you should understand what I'm saying. What I'm saying, in case of normal inductor, what you did, we made an impedance this way, J omega L, and this was enough. And we just use it in a circuit. And we had many examples on this one. I cannot continue this way because this is a different, yeah, you can say it's somehow a different device. Okay, it's so this is the formula I have to use. I have a relation between the V1. V1 is the voltage across one inductor, and I1 and I2, same thing here. I will now we will see. I have two examples. I will show you how can we how can use these two formulas in order to make to analyze the circuit in this case. If we come to transformers are actually coupled inductors with perfect coupling. So it's almost the same architecture, but here the main thing here in transformers, it's the coupling has to be perfect coupling. Okay, and so still it's coupled inductor, but here it has to be perfect coupling. But here, what you should know now, we have two different. Also, both of them almost have the same architecture. There's a small difference between transformers and coupled inductors. This is a device and this is a different device. Not different, yeah, it's two different devices. One is coupled inductor, the other one is the transformer. Okay. So this is transformer, you have to make sure it's perfect coupling. And they actually also, one more thing, they have different applications. Okay, so they have different applications. Usually, let me finish and about transformer, but both of them have different applications. So transformers here, we are gonna analyze the circuit that has transformers different coupled inductor. So here, because in case of transformer, if we have here the voltage V1, current I1, if we have here the voltage V2 and the current I2, so in case of because of the perfect coupling, so here actually we have already a relation between the voltage here and the voltage here. So V2 divided by V1 should equal N2 divided by N1. Also, I2 divided by I1 should equal N1 divided by N2. You can see I flip if it's flipped. So here 2 divided by 1, here 2 divided by 1, 1 divided by 2. Makes sense? This is the current and the voltage. And I told you, you can think now from here that, for example, if I make V2 divided by V1 equal to 10, what it means? It means V2 should equal 10 V1. What it means? It means I'm using, and you can tell now, this is a very popular way we are using transformers. So here, now I'm using transformers to step up voltage. The purpose, and that's usually use transformers. Number one, to transfer. I want to transfer power from this side to this side. I want to transfer power with different voltage. It can be a greater voltage. It can be lower voltage, depending on the ratio. Now, N here is the number of turns. Okay. So if N2 divided by N1 is greater, if N2 divided by N1 greater than 1, so that means you are going to step up or you are going to increase the voltage. I want to increase the voltage. Okay? If N2 divided by N1 less than 1, so you are going to actually reduce the voltage. Okay? That's why you can control. And not only that, the amount of power here is the same. So here if I multiply, even if you use this formula here, if I multiply I2 times V2, I2, here if you multiply if you multiply these two ratios together, okay, multiply this ratio by this, the result is 1. That N2 divided by N1 times N1 divided by N2 is 1. That means, which means, I think if you, that means I2 times V2 is equal I1 plus 1. You know from what I explained in this course, power is I times V. That means what I want to say here, usually the input power here should equal to the output power. Okay? For sure, this is a very ideal case. In reality, the input power is not exactly equal. There are some lose some power. Okay, we lose it if you can see there is some heat in the transformer because of this heat. but we try to, if it is ideal or which has to be very clear. So conclusion, what I want to see here, transformer is actually a coupled inductor, but with there's a coupled. The way, as you will see in the example right now, the way I will analyze the circuit has transformer will be different from the way we have coupled inductor. In coupled inductor, I'm going to use these two formulas, but in case of transformer, I already have two equations that give you the relation between the voltage here and the voltage here and I here and I here. And I can use these two equations to analyze the circuit, as you will see. One more thing, as I told you here, the input power almost equal to the output power, because transformers are used to transfer power. Okay, from here to here, I want to transfer power, but with different volts. And last time I told you why we need to change the volts. Okay, so I give you one example for our electrical power. Okay, what happens is that we at the generation side, so here you have generation of the voltage, and then we have transmission, and then here you have distribution. At the distribution side here, we use 100 volts, okay, or 120. At the generation, for example, you can, for example, just any numbers, but if you can have like 25 kV, usually we use here transformers, okay, to increase it to high voltage, for example, 100 kV or whatever, okay, and then we receive here 100 kV, and then we need to speed it up. So here you increase the voltage here, but you need to reduce it here. And the reason we do this way, just to reduce the losses here. Okay? Don't think nothing. But just keep in mind. So if I generate amount of power here X or energy X, it doesn't mean I'm getting X here. It's gonna be X minus some losses. So instead of some losses here, you lose some power. In order to reduce this, this loss is not good idea, or it's not good thing. In order to reduce the losses, usually if you do, we need to transmit with very high voltage. So I'm just telling you why sometimes I need to use the voltage to decrease the voltage. Okay, transformers. Any questions? Let me tell you the conclusion before I give you example. The conclusion: if the circuit has coupled inductor, we are going to use this. I will give you L1. L2, M. So you will be given L1, L2, and M. And then I will see how can we use these formulas to analyze the circuit. Number two, if the circuit has transformers, it will give you N1 and N2, N1 and N2. What is the ratio? You have N1 and N2. I already give you a gift, two gifts. The first gift here is actually the relation between V and I, between V here and V here. Also, I will give you another relation between I here and I here. So now you have two equations. Maybe you need to look for another two equations. That's it. You got what I'm saying? But you already given, you are given two equations, which you will see right now. Let's see the examples here. Yeah. So if, here in this example, here you have voltage source, you have resistance, and here is an inductor, and you can see it's very easy. You can see now these two inductors are coupled. Okay, they are coupled because you can see the arrow here and M. Okay, so this one has L1 inductance, this one L1 L2 inductance. Okay, and this one is actually this is M is a mutual inductance. One more thing you can tell now, because I give you this dot, the dot here and dot here, and you can see the current is moving this way from here to here. So the current is going to enter here, also enter here. That means as long as the current entering the two dots or leaving at the two dots, that means M you have to take it positive. When you add, I told you plus or minus. So I'm going to take it positive. Why? Because again, current here enters here and also enter. Okay? So that means the way we turn the wire is going to make the voltage induced from the other side as assisting the original voltage. That's what I'm saying. Or the voltage because of L. We have two voltages, one because of L, one because of M. M is coming from the other side. So now they are in the same polarity, they are assisting each other. That means when I use this formula here, I have to make it plus. Okay? So that's what you see. That's what you see right now. Okay. Number one. So here I'm asking you to find the voltage here. Give me the voltage. Is that okay? Please. If these two, listen to me. If these two inductors are not coupled, how I can find the voltage here? Okay, this one has an impedance, this one has an impedance, this one has an impedance. Okay, so it's easy and they are series. So I can find the total impedance. You can divide VS by the total impedance. You can calculate the current. Once you have the current, I'm gonna multiply by this impedance to get the out. Is that okay? But now I can't do that. Okay? So you will see now. Now I have to use the two formulas. Okay? So here I give you R, I give you L1, L2, I give you M, I give you VS this way. Okay, this is VS. So the first thing you need to calculate now is, I can see here, this CS, you have to make it in the complex domain. It's very easy. Number two, I will need J omega L, J omega 2, and J omega L1, J omega L2, and J omega M. Okay, you have everything. I shall look at all of this. Let's see. Now, if I apply Kirchhoff voltage law here, Kirchhoff voltage law, so that means VS is equal to the voltage drop across R. Okay, so let's I'm gonna work on the complex domain here. Okay, so VS should equal R, the voltage drop, which is I times R. Okay, I times R here. Okay? Plus the voltage drop here. I already have a formula for the voltage drop. Okay, and also plus the voltage drop. This is Kirchhoff voltage law. So this voltage shift equation, voltage drop here plus the voltage drop here, the voltage drop here. The voltage drop here in the resistor is I times R. But the voltage drop here is actually, we have a formula for it in case of couple. That's what I will do right now. So look what I did. So now I times R is going to give you the voltage drop here. Okay. The voltage drop here is actually I, the current of this inductor times J omega L1. That's what I did here. J omega L1 times R. Plus J omega W I2, the I here. But in this case, I1 and I2 are the same. Okay? If they are different, so I have to have another variable. Okay, and I think that's why I found this example is not enough. That's why I give you another example from the textbook. In the next example, they are different. But now you can see, because it's a current here, it's the same current here. So that's why you can see the voltage drop across this inductor. It's J omega L1I times J omega J omega M I as well, which is I2. Okay? Because in this special case, they are the same. Okay? Same thing, the voltage drop here, the same thing, J omega L2I plus J omega MI as well, okay? Minus VS. So now you have an equation, you know everything in this equation except I, okay? So you can easily calculate I. Okay? Now, so once I have I, because that's what I'm asking you to solve. I'm asking you to find the voltage drop here, okay? So if I know R, can you calculate the voltage drop? Yeah, this is the voltage drop here. Already we put it here, which is J omega L2I, M omega I as well. And that's what I did. Once you find I, everything, once you find I, you can easily calculate V out this way. Okay? So what I did here, guys, and if I ask you to calculate these, if they are not coupled, and I ask you to calculate this V, how can you do it? As I told you, you need to find the total resistance, the total impedance, and then you can find I by dividing VS by the total resistance. Once you have I, I'm gonna multiply it by J omega L2, and then I will get V out because they are not coupled. But if they are coupled, I can't do that, but I can use this relation. V, okay, here equal, the voltage drop here is equal J omega L I times J omega M, and in the I in the other one, in this case, they are the same. Okay? So I will show this example from the textbook. So you can see here, they are not the same. Okay. So as you see here, we have a voltage source, we have resistance, and then we have here the inductor. We have another inductor, here is the arc couple. I give you here, this is L1, L for this inductor. This is L for this inductor, and the mutual M is here. Okay. And then and here in this part, okay, you can see here we have an inductor this way, and then we have 12 ohm here. Okay. Again, I already know the voltage drop here. I already know we have a formula for the voltage here, and also formula for the voltage here. Okay. So again, number one, I need to convert the circuit from the time domain to the complex domain. Number one, I have to calculate the voltage source in the complex domain this way. 8 ohm here should be 8 ohm, the same thing. But here, for this one, it should be J omega L. This one also J omega L. And also this one is J omega M. This one M L L. Okay? Now, as I told you before, we use upper cases for V and I, which is like a convention. In the complex domain, we're going to use uppercase letters. Okay. So now I give you two formulas, or you already know two relation now. They give it to you, right? V1, the voltage across V1 here should equal I1 times omega L, this one. Okay, as you see, plus G8, which is J omega M minus I2, as you see here. Okay, so this is already given to you. Same thing, V2, the voltage here should equal J12, J omega L2 times I2, okay, plus J omega M I1. Okay. So here I1 is different from I2. So now I have two unknowns. I didn't have this one was like as easier example because I1 was equal to I2. So I also needed one equation. I only needed one equation because I have only one unknown. Okay, that's why it was easy. This one I need to find. I need because now I have two unknowns here, so I need to use. I need to find more equations. It's not enough because I don't know V1, right? So here I don't know V1, I don't know V2, right? So I don't know them. So I need to find more equations. To find more equations, simply I can take Kirchhoff's voltage flow here, and I can also take Kirchhoff's voltage flow here. This will give you one equation. This one also will give you another equation. Now we have four equations. You can find some ways to sort this. So let's see. So here I got for the voltage drop here. So Kirchhoff voltage flow here. So this voltage here, and here you have I1 times 8, and then you have V1. Okay, that's what I did. So 8 times I1 plus V1 equals this voltage. This is because of the Kirchhoff voltage law. This is one more equation. Same thing, I will get one more equation here. Okay. And in this equation, I will get this one here. V2 will equal minus 12 I2. Okay, because here V2 is because the current, maybe this part is going to confuse you why this one is negative, not positive. You can look at the direction here. This is I2 is this way, okay? And as V2, this is a voltage is negative for V2, right? But the current will go this way. And that's why we have a negative. If you know the current this way, so this one must be positive and negative. That's why it has to be negative. That's why V2 now equal negative equals I2. So if you look at this equation, and these two equations, now we have four unknowns: V1, V2, I1, and I2. I can simply try to solve them. Or so here, what we did here, I took this equation here, okay, and then I replace V1 with this one, with the V1 here. Okay, doing that, I'm gonna get this equation in I1 and I2. So again, all what I did, I just took this equation, replace V1 by V1 equal this one here, I1 and I2. Now I have one equation in I1 and I2. Okay. Same thing, I can do the same thing with the other one here. V2, I can take V2 from here. This is V2. I can just put it here. So now I have a second equation in I1 and I2. So now you have two equations in I1 and I2. That's it. So once you solve these equations, you can get I1 or I2. Once you have I1 and I2, you can do everything. So I even didn't think what they are asking for. They asking for, they need the voltage here. You need to find the voltage here. So because I'm focusing on finding the current. If once you have the current, you can get everything else. This is the main focus. Okay. So I want to find the voltage here. Okay. So the voltage here is actually negative 12 I2. Okay, that's it. So once I got I2 this way, I'm gonna multiply it by negative 12. Here. I'm gonna multiply it by negative 12. I got this is V2 here, and then I'm gonna convert it for a time domain. So to tell you the conclusion, that's the most important thing. Number one, if these two inductors are not coupled, it will be a complete. It would be similar to what I explained to you before. We have impedance and another impedance, and impedance, and then you can solve. You can find the total resist impedance, okay, and solve it this way. Here, the only way you can work here is just by using these two formulas, the two formulas we have, okay, which is V1, these two formulas. That's exactly what I did. It's the only way. Yeah, these two formulas. I have a relation between I1 and I2. V1 and V1, V2. I just use these two formulas. Okay. Please don't say the voltage here, voltage equal to J omega L R. It's not true. This is true for case if it is not coupled, but if it's coupled, you can't ignore the impact of the other one. So that's why you have to use this one. So now I have two equations. You need to find another way to find another two equations. Use it. What I did using Kirchhoff voltage law here, Kirchhoff voltage law here, and then I changed it. Then any questions? You can see here, guys, there is no voltage source or current source. So where is this current come from? Can anyone tell me? So where this current came from? There is no, for this circuit here, there is no source. Where it came from? From that. You understand what I'm saying? Yes. From that. Yeah, it's coming from the other side here because of inductance, because they are troubled. This is because they are connected. But they are not connected using one. It will transfer energy from here to here. You got what I'm saying? Any questions? Anyway, so now I'm gonna move to the next one here in case of transformers. Maybe it's easier in case of transformers because in case of transformer, I already give you already have two relations. Okay, either in the time domain or complex domain, these two relations are gonna work, which is V1 divided by V2 would equal N1 divided by N2. I1 divided by I2 is actually N2 divided by, you switch. See, with this one, 1 divided by 2, 1 divided by 2. This one, 1 divided by 2 is 2 divided by 1. Switch. Okay? Anyway, so again, you will see now it will be what happens here. I'm not gonna see this circuit here. We have a voltage source, and you have a resistance, and then you have a transformer. The transformer has a coil and has coil here and another coil. Okay, and this is a transformer, and then you have R2, and you have an inductor. This is a normal inductor. It's not coupled with anything with anyone. Just normal inductor. Okay. So how I can solve a circuit like this one? Look here, guys. Number one, similar to what we did before, like R1 here. Every here I have to transfer it to the complex domain. Okay. So this voltage you need to transfer it to the complex domain. R1 should be R1. R2 should be R2. If you are a capacitor, also I'm gonna replace it by Z. In this case, I have an inductor here. I'm gonna make it Z. So everything here is similar to what we did before. What about how do we achieve the transformer here? Okay. So the way I'm gonna deal with the transformer is already using these two equations. You got what I'm saying? So yes, I have here E1. E1 is the voltage here. I have E2 here, and I have I1 and I2. And I already have a relation between I1 and I2, E1 and E2, because I give the ratio here. The ratio is given to you. You got what I'm saying? So you don't need to do anything here other than you already have two formulas you can use. So let's see how can we again you can calculate Kirchhoff voltage law here and also Kirchhoff voltage law here to get equation here, another equation here, and you already have two more equation. See, this will make things easier after that. Okay, so here as I told you, this is, don't be confused, this is a normal inductor, single inductor. So this one actually is going to be like a resistance and impedance. This impedance is J omega L2 this way. And then also this voltage, you have to convert this from the time domain to the complex domain this way, as I said. So now let's see. I told you we already have two relations. E1 and E2, I1 and I2, we already have them here. Okay. So what I'm gonna do now, guys, I'm gonna apply Kirchhoff voltage law here and Kirchhoff voltage law here. That's it. Once I apply Kirchhoff voltage law here, I will get two more equations. After that, I will see what can we do. Okay. So if you apply this Kirchhoff voltage law, so here you can see negative Vs equal to I1 times R1 plus E1. E1 is unknown. Give it unknown. Okay. Because I have a formula for it, or I have, sorry, relation here. Okay. Anyway, same thing here. If you apply here, so this one should I2 times R2, okay, plus I2 times the impedance here, okay, minus E2, minus, because you can see here the current, I'm assuming this is the direction is this way. Here I'm assuming the direction is this way. So here you are encountering the positive current. Okay? Okay, so now how many unknowns you have? I have 4 unknowns, which are I1, I2, E1, E2. And how many equations now you have? I have 4 equations. I have 4 equations. It's easy. You don't need this one. You can do it manually. It's not difficult because these 2 equations are very, very easy. Anyway, so here, yeah, I just we plug in the numbers here. After we plug in the numbers, this is the first equation you have. Yeah, this is the first equation you have. Negative E2. I didn't do anything. I just plug in the number. Okay. So here, negative E2 equal this is a equation between E2 and I2. Okay. And yeah, so it's negative E2 and I2. Now I can this is a second equation. No, so all what I can do here, I can replace, I can, this is E2 and E1. This is the E2 and so E2 is actually 2 divided by E1 from here. So now I can make instead of E1. And now instead of I2, I can make it I1 this way. So now I have equation is actually between E1 and I1. Okay. I can do the same thing for the other. So here I did this one for the first equation, which I got it from Kirchhoff voltage law here. Okay, I already have a second equation here. So also, yeah, this is second equation. The second equation is already sorry, the first equation is already I1 and E1. So now okay, so here's the first equation was I1 and E1. The second equation was I2 and E2. But it's easy. You can E2, you can replace it by E1 this way. I2, you can replace it by I1 this way. Okay. So now I have 2 equations that in E1 and I1. Okay. This is the first one. This is the second. Okay. So now after that you can solve this equation and find I1. So once I find I1, I can easily find I2. I can use this formula. Once you find E1, it's easy to get E2. But let me see what we are asking here to find V out here. Okay? In order to find V out here, so I need to find the current I2. I'm gonna multiply I2 times the impedance. So once I find I2, so here once you get I1, you can get I2, or you can solve it for I2 directly. So whatever it is. So anyway, so you need I2. Once you have I2, I'm gonna multiply it by this impedance to get it. Any question, guys? So let me summarize what I said, just to make it easy. What I'm saying. Already you have two equations. Okay? I know the calculations are daily because you work with complex numbers. This again, and I mentioned multiple times before, this is the only difficulty I see in this chapter. Other than that, I didn't teach anything new except almost everything is we just use the same stuff I explained. Okay? So here what I'm saying here, to make things easy. Number one, you already have two equations, which is E1 divided by E2 equal N1. I'm gonna give in this kind of equations, I have to give you N1 and N2, or I have to give you the ratio. And you have I2 divided by, so I already here between two circuits, I know the relation between I1 and I2, E1 and E2. Okay? And then you can apply Kirchhoff voltage law here, Kirchhoff voltage law here. Now you have put the just solve for whatever you want. Any question? My advice to you, if you read the examples, okay, you may think, yes, I can go to the exam. But in reality, that's not enough. When you come to the exam, even if I give you the same example, you're not going to be able to solve it, especially for this chapter. For this chapter, you have to do all the calculation by yourself. Okay, it's your responsibility to practice. How can you work on using complex numbers? And if you have a good calculator, this will make it much easier. Okay? Any questions? Yeah. Let me just tell you what we have done so far. What's fun as well. Okay? What we have done so far, number one, we analyze DC circuits. When DC circuit, when any current source or voltage sources, okay, are DC. DC means they are constant over time. Okay. And then starting from the last chapter, I started to explain how can you analyze AC circuits. Okay? In AC circuits, any current source or any voltage source are actually sinusoidal. So that's cosine of sine. They are sinusoidal. Okay. This change over the time, especially you are focusing on the sinusoidal voltages or current. This can be voltage or current. Voltage or current. That's what I explained in the last chapter. In the last chapter, my focus was how can you calculate the voltage and the current, okay, and also impedance, the equivalent impedance. This was the main focus in case of AC circuit. But I did not talk about power. How can you calculate the power? And this is actually the topic of the next chapter. Okay. So the next chapter or the chapter I will start right now, it's just a continuation to this chapter, but I will focus only on power. How can you, for AC circuits, how can you calculate power? And we have like a big story compared to the way we did power before. What I'm saying? So again, I'll say it again. The chapter I'm gonna start right now, guys, is I'm gonna talk about AC circuits. How can you calculate power in case of AC circuit? You will find something, but why you need a complete chapter for that? Okay, because the story is bigger than what we did before. You will see for sure some similarity to what we did before. Also, there are some different. So I just want to remind you what we did before. For example, if you have a resistance this way, and we have a voltage V, and we have current I, and here R. You remember we said the power should equal, same thing if you have a source, and you have here R. Okay, this is V, I, and R. So we said the power should equal V times I. Okay. Or also, it's the same thing, because V equal IR. V equal IR. So if I do some simple manipulation here, you can find, also I can say I square R. So another way to calculate it. So in this is circuits, power equal V times I here, or I square R. So if you have I and R, I don't need to calculate V, just I square R. Okay. Or V squared divided by R. Okay. So again, they're the same. All what I did here, I just replace. I replace V by IR. And to get this formula. But to get the other formula, I just replace I by V divided by R. I got this one. So they are the same. Okay. Any question, guys, here? Okay. Now I want you to understand, okay, how this will be different in the case of EC. Okay, I will let you know. Look here, guys. In case of DC, the voltage of the current, this is the current is constant this way. And the voltage also is constant this way. This is DC, right? That means when you calculate the power, and power equal V times I, also it will be constant this way. Make sense? V equal VI will be constant this way. This is in case of DC. Okay, what is your no? AC circuit is because of the front stone. Because in case of AC circuit, current is going to be sinusoidal. Also, for example, this is I. This is a voltage. Also, this one will be sinusoidal as well. Okay? So we need more investigation now. Okay, that's why I will explain how this one will be different. It's still, as you would see right now, one way to calculate the power is actually V times I. If I multiply V times I, and this one is called instantaneous power. So this one way to explain it, to do it. So I want you to understand, guys, here, if I is this way, and the voltage, for example, this is I, and this is the voltage, that's voltage this way, for example. That means the power, because this one, it changes over the time, this one also changes over the time. The power will be the same thing, because actually the power is, for example, at any specific time, I'm going to multiply this I by this V. That's why we have what we call instantaneous power. Instantaneous power is equal to V times I. So that means every moment the power will be different. Because the power is still V times I. Okay, so the power will be different. Okay. One more thing to number one here, I explained what we call instantaneous power. So that means the power at each instant. Okay, or the power at each moment. Okay. And this can be done simply by multiplying IT times VT to give you the instantaneous power. And usually this will also be EC. That means the power changes from one moment to another because I changes and V changes. I changes and V changes. Make sense? So this is one thing. The other thing is, this is one difference. The other difference is that sometimes you are interested on the average value. Sometimes if you have something that changes over time, I'm interested in the average value. Okay, so that's why here, as you see, well, the second thing we can calculate here. So here I can give you the instantaneous power. Also, sometimes you are interested in the average power. Okay. We didn't have all of that in case of DC. In case of the DC, just V times I. No, here we can, maybe I'm interested also in average power. Okay? Average power here is actually the average is equal to 1 over delta T. Okay, but it's from T1 to T4. D. Okay, so here. If you have, for example, a signal like this one, okay, whatever the signal is, okay, whatever the signal is. So here you can calculate. I will show you now how. So here I'm taking only so usually we take it at one period as you will see right now. is the beginning time last time, B dt. Okay, so this is instantaneous power is here. This is the power change over the time. By this way, I can get the average power. Okay, you will see. So this is another. You example how can we do it? But it's a formula we have to use. Sometimes our one definition here is PC. I can calculate instantaneous power, and this one is just function in time. Because every moment, the thing will be different because I different, be different. We didn't have that in DC. That's number one. Number two, also, sometimes we are interested in the average amount of power because power it changes. So we need to, sometimes we're interested in the average. We are going to use this formula to calculate the average as well. Yes. One more thing also, which is very interesting, because as you will understand in details, we have a current here. This current, sometimes it is positive, sometimes it is negative. Okay. Same thing here, okay, whatever, same thing here also for the voltage. Sometimes it's positive, sometimes it's negative. And power is actually I times V, I times V. That means, as you will see, that means the power, it's not only, it changes over the time, it's not constant, just every moment we have different power, right? Not only that, but also the power can be positive or negative. Again, this is something we didn't see before. Okay. So power itself can be positive or negative, and also every moment has different power. So let me tell you. So what do you mean by the power is positive and how the power can be positive and how the power what it means? Okay, you will understand in details, but I just wanna show you how what I'm explaining now is different from what I did before in case of ET. How power here would be different from the power explained before. Okay, now the power can be positive or negative. So if you have a source, for example, and you have a load here, if the power is positive, that means it's the power of, we are transferring power from the source to the load. This means it is positive. Okay, but actually, if the power is transferred from the load to the source, that we say negative power. You got what I'm saying? So here, if the power is positive, that means we transferring power from the source to the load. But if it is negative, that means we are transferring power from the load to the source. Okay. Again, we didn't see something like this in this. Okay. Someone can ask me how the load is gonna provide power to the source. Can anyone tell me? It doesn't make sense. Something here doesn't make sense, right? How the load is gonna provide power to the source? How this can happen? The load has power, already has power, and then it's gonna give this power to the load. Any answer?
Capacitor, right?
Hmm?
The capacitor reducing energy.
Yes, this should happen if the load is storing energy. If you have a capacitor, if you have inductor, and the capacitor is storing energy, so now it can release energy to the load, to the source. You can think. However, when I teach more, you will understand. If this one just a resistance, it will be positive all the time. So anyway, you will understand it. But I just want to show you how what I'm explaining now is different from what I did before. Number one, there is something we call instantaneous power because the power should be changed. It's still similar to what we did before. Power is actually V times I. It's the same things. But here, because the V changes and I changes, the power also will change. That's what we keep in mind. Also, sometimes we are interested in the average power, not in instantaneous power, average power. Also, power now can be positive and negative. Positive means from the source to the load. Negative means from the load to the source. Anyway, so now okay, so here in the very beginning, I'm explaining instantaneous power, okay, which is actually V times I, okay. So V is function in time, I function in time, so P also will be function in time, okay. Second thing, as I told you, we can also calculate what we call average power. The average power, as you see here, actually 1/time. And I'm gonna tell you, usually this time you are gonna
Billion, billion. 1 billion should be enough. If you, even if you calculate the average of 2 billions, which is the same, like 1 billion, that's why 1 billion.
1/the period, and then here this is the time. B, this is the instantaneous power. DC. If you use this one, you get average. I think I'm having here. I give you here one example, but this is not sinusoidal. So, but again, this formula can be used for anything. But again, as you know, this source, we focus on sinusoidal signals because actually most of the signal we have in our life are sinusoidal. The power come to our home here, to our homes. This power is sinusoidal. Communication also sinusoidal power. But this is a general formula can be used for anything. So here in this example, you can see here is a voltage, and here I connected to a resistance here. Okay, so actually the power here equal V times I. Okay, and I is actually V divided by R. So here I can say the power is V squared divided by R. The power is V squared divided by R. This is an instantaneous power. In case if R here is just a resistance. Okay? And this is V. So I give you V here. This is V. So if I want to calculate the average value, okay, so it is enough to calculate the average for 1 period, 0 to T, 1 period. If you calculate over 2 period, it will be the same. If you calculate over 3 period, it will be the same. That's why it's enough to calculate only. So I can just apply this formula we have here. Okay. So it should be 1/T. Is the period, 1 period. Okay. From 0 to T, here to here, from 0 to T here. Okay. That's it. It's here. And then you can just apply the formula. You can split it from 0 to T. Here's the power is 0. Here's the power is 0 because the voltage is 0. That's why you can see here is 0. So here I'm gonna only take from 0 to T divided by 2. So here I split from 0 to T divided by 2. I have some power, but from T divided by 2 to T, 0 because the voltage is 0. And then if you just follow the calculation, you find it is the power here should be V squared divided by 2R. Half, because half of the time. So it's not V, it's gonna be V is the capital V here, it's the DC value here, whatever you have here. Okay. Because half of the time I have power, the other half I don't have power. Okay. So if you see how the power here looks like, should be again V squared divided, so it should be V squared divided by R. So the power will look like something like that, but the value will different. But the power will be something like that. Here we have some power and then 0. Have power 0. That's why I'm interested in the average value. Anyway, so whatever it is. And then here again, I'm telling you, if you just take it, it's enough to take it over 1 period because the average you calculate over 1 period will be the same if it is 2 periods. So 1 period should be enough. Okay. So again, I will give you. So now at least I just want to tell you here we have something we call instantaneous power. Also we have something we call as average power. Okay. As also I'm gonna explain in details if you have here I equal to IM equal line omega T plus theta I psi is the angle for the current. Same thing if you have V of T, this is the instantaneous current, the current is the voltage of it. This one should be VM cosine omega T plus CV. Okay, sorry, theta V. Okay, so now if you have the instantaneous power, you just multiply these two together. Instantaneous power, just multiply them together, and I will do that. But if you want to calculate the average power, the average power is equal to VM IM divided by 2. Okay, if you apply the formula we have before and you want to find the average power, cosine omega V minus omega theta V minus theta I. This is the average power. VM times IM divided by 2 cosine theta V minus. Anyway, I will give you more details, but just what I want to see now if you want to calculate the instantaneous power, I have to multiply these two together, and I will do that shortly. Same thing, if you want to calculate the average power, you have to use the formula I explained, and if I use it and if I do the algebra manipulation, you will find this is the last formula we have for average power. Before I give you more details, I wanna come to definition. We have something we call it the RMS value. R here means root, mean square, root means square value, or sometimes we call it effective value. So what do you mean by that? So now I want to, this can be RMS for voltage or current. So here it can be RMS value for voltage or RMS value for current. Okay. So I just want to explain what this means. It means, for example, if you have here an AC source, and then you have here a resistance this way, okay, we have current this way, okay. And now if I have another DC source, it's the same resistance R, so resistance here is the same, but here the current here is a DC current. Here for sure this is DC current. Okay. We already know here the power here delivered to the resistance is actually I square R. We're gonna call IDC. Okay, so IDC square R. This is the power delivered in this case. Here, the power delivered here is actually I square R, but this one is actually instantaneous power. Okay. So again, I want to make a definition now. What is the definition? What is if you have I? This is I here, okay. And we have what we call VM. Sorry, IM, the maximum value, IM. I wanna calculate the effective value for I. I wanna calculate the RMS value of I here, or I wanna calculate the effective value of I. So what this means? What it means when you have a sinusoidal signal like this one, and I wanna calculate the RMS value of this one. You already know the peak value. This is the peak value, maximum value, right? We know it. So this is the peak. Okay. But there is something else I can calculate. We call it the RMS value of I. By the way, same thing I can do for voltage, I on voltage. Okay. Also, it's something we call effective value for I. What it means? What it means? Simply it means here. What is the average value, average power here? Okay. So here, I'm going to calculate the average power here. And I will look for IDC that is going to give me the same average power, but here in the DC. Okay, so make it very clear. So for example, here is RMS, for example, it's equal to 1 ampere. What it means? It means this source is providing R with average power, which is actually equal to if I have a current here of 1 ampere. Okay, so the two circuits have the same average power. Okay, so again, that's what we call RMS value or effective value. So effective value means what is the value of DC current that can give the source the same amount of power giving each other. You got what I'm saying? So this value we call it RMS value. And to make it very easy, this value is actually in case of I will give you a formula. The formula will depend on equal, right? So all I will do here, this is the unknown. I need to find ITC here in this case that gives me the same average power we have here. Okay. So I will choose the formula, but just this value, because again, this value may be different if the signal, based on the shape of the signal, but because we're focusing on sinusoidal, where the maximum here can be IM, or the voltage here can be VM, in case of voltage or in case of current. So in case of sinusoidal, the RMS value for the current here is actually Im divided by square root of 2. The average value here, the RMS value here for this one is actually Vm divided by square root of 2. Which means if you have a DC voltage, okay, that provide the current equal to this current, equal to Im divided by 2, so actually this source will provide the same power provided by the DC by this current, DC current. You got what I'm saying? Yes. And by the way, let me ask you a question. When you know how much voltage we have in the wall here, how much voltage we have? 110, right? Or 110 or 120, right? 120 volts. Okay. And we agree, you know the power we have, sinusoidal power. So what this value is? What's 110? Is that the big value? That the big value is 110? Or what is this value? Actually, this value is RMS value. You get what I'm saying? So here the 110 we have in our homes voltage. This is actually the RMS value for the sinusoidal voltage we have. It's not the peak. Okay? It's the RMS value. Again, I will before I show the slides, but I just want to tell you here. The RMS again, if you have a sinusoidal signal like this one, there is something I can calculate. It's called root mean square or RMS or effective value. Okay, we can do it in case of voltage or current, and this one should equal to. There is a proof for that. Just you plug in a formula as you can see. Vn divided by square root of 2 or In divided by the second. The meaning. What is the meaning? The meaning of it is. If you have a DC source that here for the if I have two circuits, one circuit using this current and another circuit, the current is actually Im divided by square root of 2, the two circuits will provide the same power. Okay, so in case of DC and AC. Anyway, I will show you here. Where is it? Again, here I'm explaining the definition, RMS or effective value for a periodic signals. Okay. I told you the power here is I square R. I squaring this I is DC. This I here is up. I here is AC. Okay. So here I'm looking for what value I have for R. So the average value, this is the average value, okay? The average value for the power equal to the power here. Okay? That means I square R here, the power delivered to this source here, equal to the average power here using this formula. Okay? Anyway, so you just make it equal and you try to find DC, what is the value of DC that can make it equal. So at the end, you will reach to this formula. IDC should equal square root of 1 over T integration from 0 to 2 I square T. This is a general formula you can use it for any signal. Signal is a square signal, sinusoidal. This is general. If I apply this formula for sinusoidal, it becomes what I told you. I maximum divided by square root of 2 or V maximum divided by square root of 2. That was the effective value or RMS value. Okay. So here the reduced current IT works effectively the same as the DC current in terms of given power. This is the meaning of RMS. Yeah, here. So here I can apply this formula in case of square in the case of this signal. But again, I may not care much about this signal. So here, if I apply it here, you can find RMS is I divided by 2 for this signal. Okay. But again, we don't care much about this one. We care about sinusoidal. So if it uses this formula here for sinusoidal, sinusoidal signal equal Vm divided by square root of 2. Or if it's a current, whatever it is current or voltage, it's the same thing. It's going to be I maximum divided by square root of 2 or V maximum divided by square root of 2. Okay, guys? So anyway, so I'm going to yeah, for example, here Yeah. For example, here, if you have a signal like this one, okay, this is the maximum value is 6. Okay. If you want to get the RMS value, you are going to divide it by square root. There's one thing actually it does not confuse you. Or let me. There is a small thing here, hopefully it does not confuse you. Look here, guys. If you have Vm, for example, cosine omega c plus beta, we agreed when you convert this one to the complex domain, we agreed on that. It has to be, okay, Vm with angle theta. Is that okay? That's what we did. And when you come from the complex domain, you come back to the time domain again, it's gonna be actually whatever, it's gonna be the same thing. For example, if I get here 5 with angle 20, okay? So number one, what I did here, I'm gonna do the opposite here. It's like the same, right? So when I come back to the complex, to the time domain again, okay? So it's gonna become like 5 cosine. I need to add omega t plus this angle 20. Okay. So number one, here I'm gonna take only the real part. I'm not gonna take the imaginary part, only real part. Number two, here, when I move to from here to here, I actually removed omega c. So when I come back, I have to put it back. Okay. So anyway, that's what we did. Okay. In this chapter, we can do the same thing similar to what we did before. Okay. I want to pay attention to this point. Hopefully, it doesn't confuse you. Okay. So again, we can do the same thing here in this chapter. We can do the same. That's what actually what happened in the textbook. In the textbook, they do exactly the same thing here. Okay. It's okay. You can do that. However, in the slides, okay, in the slides, we're going to do something different. Okay. What we are going to do is if you have Vm cosine omega t plus theta, when I transfer it to the complex domain, I'm gonna make it Vm divided by square root with angle theta. Look here, there is no square root. Here I put the maximum value. Here I put the RMS value. Okay. You can just put anything here. No, I will consider it when I go back as well. Otherwise, it's not gonna work. Okay, so when I go back from here to here, for example, I got here 5 with angle 20. What I will do here when I move from here to here, because here I divided by square root, also I have to multiply by square root. You can finish what I did. Look what I'm saying. So 5 is square root here, and then cosine omega t plus 20. Okay, guys. So again, let me tell you what I did, because here again, when you move from time domain to the complex domain, what we have done before, you took Vm this way. And when you come back, I will take this one like Vm as well. There is another way to do it, and that's what we are gonna. This is in the textbook. Listen to me. In the slides, okay, what we are gonna do is when I move from here to here, I'm not gonna use the maximum value. I will use RMS value. And when I do the opposite, I will here you divided by square root, I will multiply by square root. Is that okay? That's why you always, any formula I will in the slides, in the textbook, you will find there is always a difference of square root. Okay, I will show you, but I would try to use any confusion, just to make a calculation easier, because all the time we have a square root. So instead of carrying square root in most of formulas, we can just we can make it more simpler. But again, because what we are doing here, I did the opposite. When I go back, it's the same thing. Whatever you do, I can do the opposite. You have to say, I'm not saying the numbers you have in the textbook will be different. No, we're gonna get the same numbers. What I'm saying. But the formula will be little bit different. Okay. For example, just to understand what I'm saying. For example, here when I will calculate Just an example. So here, when as I'm gonna explain next time, when you calculate, when you calculate the power, I will let you the power. I'm gonna in the slide. I will tell you the power equal V times I active. You know this factor means conjugate of I. You still, so here's the way I can calculate the power. You multiply V times I in the complex domain, but I have to be conjugate of I. V times the conjugate of I. So I will tell you V is equal V I asterisk, okay, divided by 2. They're the same. One, because this actually V maximum divided by 4. This one here is actually. This V here is V maximum, okay? Here I maximum divided by 2. But if you look here, this one V maximum already divided by square root, and this one I maximum divided by square root. So actually, so the first one, this one to maximum is going to be the same. Okay. Anyway, so what I want to tell you here, guys, we're gonna make a little bit change when you convert the times. Okay, and because of that, the formulas in the complex they look different, but when you make it in the using maximum, they will be the same. You get what I'm saying? But anyway, I will see you next time.